Okay, so our last speaker is David Nagib. David is from Ohio State University, has developed a very effective program related to CH functionalization involving radical chemistry. It's characterized by being, I think, extremely original and really interesting, the full scope of the new types of opportunities developed with this program. And so we're delighted to have you, David. The title of the talk is Remote, Double, and Selective CH Functionalization via Radical Chaperones.
Thank you very much, Hugh. Thank you for both an overly kind introduction, as well as the opportunity to come back to this setting and participate in this extra special virtual symposium. So some of you might already know that I had the opportunity to give a talk in late 2018 in this setting. And so I decided to give you a little bit of an update of what our team has been up to in the last 2 years. And so you'll see the top 3 words at the top describing maybe the unifying theme of this talk. And I'll just jump on what Alison Winlet mentioned earlier, a really great description of CH functionalization as really being the field of finding selectivity. So the secret sauce for us to get to that selectivity is using this century-old reaction, first reported by Hoffman in 1885. I just went back and read the German paper today, thanks to Google Translate, which describes this molecule subjected to these conditions loses 2 atoms of hydrogen, and that's about it. Thankfully, a few years later, Loeffler and Freytag, actually, Hoffman also mentions that the molecule looks like piperidine, but is not quite piperidine. so later, Loeffler and Freytag determined that it was this 5-membered variant. And here are the conditions from a century ago. You can see they're not the sort of mildest, most modern conditions that Magnus would like to use in an industry setting, taking chlorine gas or bromine, subjecting the amine to neat sulfuric acid and refluxing. And as one does, after displacing this NOx bond and forming a delta CX bond, an acidic reaction needs a pretty basic workup, and that's what deprotonates the amine here to displace it and form the ring. So of course, we now understand this mechanism and where that selectivity comes from, that functionalization of just the delta CH bond occurs via 1,5 hydrogen atom transfer, which is both entropically and enthalpically favored. And then we also now appreciate that neat sulfuric acid was not by chance. The protonation of the nitrogen as a radical cation is really essential for high reactivity. And so if you're interested in learning a little bit more about this, Leah and Koki wrote a really nice tutorial a few years back, cited here at the bottom. But what you'll find nowadays is if someone wants to do this HLF transformation of a delta CH bond, you're more likely to use the Suarez variant that uses these hypoiodidates that are formed in situ from iodine and hypervalent iodine. And then these nicely can form a weak Ni bond that can be broken by visible light. And then of course the delta Ci bond is a better leaving group, and these can be cyclized down as well. And it's the same type of regioselectivity, but you'll see now there's a neutral radical. So it's a little bit less reactive. What Suarez showed us was that you need a little bit of a withdrawing protecting group to polarize this nitrogen-centered radical. But even so, there's a limitation that I introduced here. You can see these weaker benzylic CH bonds tend to be the limitation. And that's simply what we imagined to be a function of all these other weak hydrogen atom acceptors that can abstract the weak alpha amino CH bond. So this was actually the very first problem we set out to address years back with Ethan and Stacy. Just can we apply the HLF reaction to secondary CH bonds? And so their proposal decided was if you're going to shine visible light in the Suarez method, you don't want to start with iodine that can break. What we decided was we started with iodide anion. And now we have in situ oxidant that can form iodine, but also this iodide can sequester the I2 as triiodide here, as you commonly see in electrochemical flow cell battery type thing applications. So I think a picture is worth 1,000 words. In green here is the NMR spectra of the pure pyrrolidine product, where the 3 alpha amino CH bonds are these 3 diagnostic peaks. And in blue here is the crude reaction using this triiodide strategy. You see a whole lot of product and not much else, really exquisite regioselectivity. And then of course in red here is the sort of classic I2 mediated conditions where there's some product, but a whole lot of other things as well. And so just kind of showcasing some of our favorite substrates from this first example of a secondary CH amination in the presence of weaker CH bonds, really on the left-hand side, I highlight with these gray circles here. In all cases, the weaker CH bonds are left untouched in the presence of the secondary selective delta amination. And so what can you do with this type of transformation? We love hearing from practitioners of the chemistry. One example we recently heard was from a med chemist interested in the 2 aryl pyrrolidines that we made. I found it peculiar because you could already make them using the old-fashioned Suarez conditions. You just simply put an aryl group 4 carbons away from your amine and that'll close down. But what you can see here is the starting material synthesis is a little easier now. You take these benzaldehyde-derived imines, just add butyl lithium into them, and now with the secondary selective aminations, you can get to the same types of products, albeit via opposite disconnections. So that was sort of a warm-up for us to get interested and sort of wrap our hands around the HLF reaction. We weren't actually really interested in the CN bond formation. At the outset, we were really curious about could we intercept this HLF precursor or intermediate to generate CC bonds. And so this was the work of Zhu Zhao and Leah with the idea here after you break that Ni bond and after 1,5-HAT, instead of these 2 radicals recombining, could we intercept it with a nice radical trap like an acrylate and generate this CC bond? So long story short, the answer was no, we could not do that. What we understand now is that the recombination of these radicals to form CI essentially has a barrierless transition state. And really to showcase that for you, we once used acrylate as a solvent and we still did not observe the CC bond formation. All we saw was CI formation. And so when you're fighting even the solvent as a radical trap, that makes you kind of step back and rethink your proposal. And so as we were doing that, it turns out we were not the only people interested in interrupting this century-old reaction. At exactly the same time in back-to-back papers, Knowles and Rovis showcased that the solution to interrupt this reaction was to not have the halogen radical in there in the first place. They made the N-centered radical directly from an NH bond using base and oxidant via these proton-coupled electron transfer strategies. But fortunately, our inspiration was from the work of Liu, as well as Stahl and Liu, taking these NFSI oxidants, these weak NF bonds, can be reduced via copper catalysts to generate these N-centered radicals that they've beautifully shown can go on and do intermolecular HAT transformations. And so what we had hoped was, could we map this on in an intramolecular sense? So if you can see here, if you just remove one of the withdrawing groups on NFSI, you would have these tosamid protected amides. And we wondered if we could affect the same types of reactivity for selective remote functionalization. So again, the short answer is no. The same types of copper catalysts don't reduce these oxidants, which are just not as strongly oxidizing as NFSI. But what we found was actually really nice. If we have the right ligand on copper, so we can transmetallate an aryl group with aryl boronic acid onto copper, now we have a stronger reductant that can in fact reduce the NF bond. And after 1,5-HAT, you now have this remote carbon radical that can intercept this copper aryl species. And you can imagine a quick reductive elimination might give you a delta C arylation product. And so that's what we did. I love this use of aryl boronic acids allows you to go to the shelf and grab a bunch of arenes and heteroarenes and have a really nice scope. But also we're interested in regioselectivity a lot. So I mentioned the 1,5 selectivity is pretty robust. Here it is favored over 1,7 selectivity, even though this benzylic CH bond out here is about 10 kcals weaker. Here's the delta over an intermolecular when you have 2 benzylic positions. And then here's maybe my favorite molecule in the whole paper. There are 33 CH bonds and we've arylated a single one of them. And so of course I say that, but I now realize that that's not completely true because we did this racemically. And so of course there were 2 CH bonds that we potentially arylated. Of course, when it's the first remote CH arylation, that's pretty cool on its own. until Zhu showed me this fun result that he'd been working on the side here. But using these chiral ligands, you can actually affect some decent levels of enantioselectivity in this remote delta CHR relation. Of course, the problem with radicals is sort of controlling stereo induction is pretty hard to do. And I show you here a lot of trial and tribulation and really just the absolute best enantioselectivity we could get for the remote aerolation. But we're not undeterred. This was still a pretty neat way to introduce an aero group pretty remotely. Of course, it didn't escape our attention. Actually, Leah pointed out one day that these CH bonds at the delta position are now benzylic, and so a little bit more activated for the HLF. And so we could do a two-step sequence to make a whole library of these two aryl pyrrolidines as shown here via this sequential delta CH functionalizations. So I'll sort of step back here and kind of show you what we've done with our remote aerolation compared to one of our other favorite aerolations in the literature, this one coming from the lab of Melanie Sanford at the school up north. And so you can see here, we've used copper, they use palladium, we've used an aryl nucleophile, they use an electrophile, and of course we have this 1,5 HAT mechanism compared to their palladicycle directing. And so basically, the theme of this slide is it's complementary in every single way. And I absolutely love that. And that's maybe the single biggest driver of what kind of projects we tackle. So a little bit of opportunity for radical chemistry. Of course, we can also look at other problems and challenges and be inspired by them as well. So here's a piperidine core. These 6-membered rings are actually the most common heterocycle in all of medicines, and that intrigued us as well. So we thought about tackling, essentially moving from pyrrolidines to piperidines, but I've already mentioned to you, and Zhu and Xin certainly realize this, that 1,5 HAT has a century of actually selectivity principles behind it. And so rather than try and go after a 1,6 HAT, what they decided instead was, let's add a cyano group. This can serve as a carbonyl precursor, putting that at the delta position and then cyclizing it down, might access piperidines in a different fashion. And so here's an example of that, using instead of an aeroboronic acid now, a TMS cyanide as the nucleophile, and also that ligand that makes the copper a little more reducing. And that can install the delta cyano group, a little bit more regioselectivity probes to show you. 1,5 over 1,6 is pretty robust, over 1,7, and over these allylic CH bonds a little more remotely. And then of course we can add arenes and heteroarenes at that remote position to test our next hypothesis, which is to say, could these cyano groups serve as linker groups to form the piperidine scaffold? So a little bit of diball reductant unleashes the aldehyde, which can then cyclize down, forming this hemiaminal, which we can then reduce with a mild silane reductant, or we can add nucleophiles into that hemiaminal carbon. But just taking a look at that simple silane reduction, you can see here that the enantiospecificity is pretty high, where that C3 stereocenter that we have set remains set like so, including in one of those molecules that I had shown you previously that turned out to be the core of this anti-cancer therapy from Merck. And so just kind of summarizing the delta chemistry, I've shown you the aerolation and cyanation, where the cyanation certainly had better enantioselectivity, although we're certainly still working on getting that EE up for aerolation as well. And then we've shown you the two-step protocols that we've developed for turning these acyclic amines into heterocycles as well. So the field has certainly exploded, if you will, in the last couple of years here, using these NF strategies or directly from the NH. You've seen a variety of really neat delta CH functionalizations and really just compounding lately. So it turns out that the late great Muñoz also had a really nice combination of the intermolecular amination followed by an intramolecular HLF to generate two aryl pyrrolidines. And so I also wanted to highlight that really nice work as well. And so looking forward, what the team is currently working on, still unpublished, but this is the work of Leah, Ross, and Allison reaching the final stages here. I mentioned to you that the ligand on copper is really important to reduce the NF bond. And so one way we've been working on to get around that is using these iridium photocatalysts to reduce the NF bond, and then simply after HAT, trapping with copper and any type of ligand we want. And so when we look at lots of ligands, we've found some classes will do interesting chemistry like regioselective beta hydride eliminations to remotely install desaturation as we like. And of course, we can do that second functionalization again, now to access whatever types of heterocycles we like, or remote double stage functionalizations. So that concludes the delta CH functionalizations of amines. Now I'm going to pivot pretty strongly to our chaperone work, the functionalization of alcohols that Ethan and Koki had developed, with the idea here that that end-centered radical could also be appended onto an alcohol. And then those same rules of 1,5-HAT selectivity and different types of functionalizations, as I've shown you, could be used to functionalize alcohols at different positions. I just show you here the beta functionalization in the case of the blue circle being one atom. And so this sort of stands on the shoulders of many giants in the fields of CH functionalization, interested in using alcohol as one of the most ubiquitous functional groups or handles to install a directing group. I just highlight some of our favorites in the field of metal CH functionalization, predominantly putting on nitrogen containing ligands that can coordinate onto palladium or another metal briefly. Of course, there are certainly some fantastic radical precedents. Even from the year of my birth, Ron Breslow was interested in functionalizing steroids with these sort of installing an iodine radical or some other radical onto a steroid and having it reach around. But here was our simple extension. Our thought was if we could take an imine, condense it onto an alcohol, generate a hemiaminal radical in situ, we might be able to just eventually just take off this group, the so-called chaperone or director of radicals in a regioselective fashion. So first generation, the imines didn't quite work. They were sort of always prone to these unfortunate beta scission products. Essentially in all cases, we always got these quantitative formations of these imidates. We recently, or I guess not so recently, now a year ago, wrote up essentially the whole story of all the different R groups we'd ever tried. But the story I want to just bounce off of today is that we one day decided if we could make these imidates in such great yields, why not just use them to direct intramolecular HAT? And so long story short, we make these Overman style trichloro acetoimidates here. On these alcohols, we use our triiodide conditions to direct CH amination to the beta position, forming these oxazolines. And then an acidic hydrolysis simply exposes the beta amino alcohol. A nice acid-base workup allows you to access these in a chromatography-free set of protocol, basically, to get from an alcohol to an amino alcohol in just one afternoon. And so I'll just show you here what we've learned since then. These trichloroimidate radicals are exquisite for benzylic CHs, where the arene or heteroarene weakens that CH bond. You can see here really great diastereoselectivity in the case of secondary alcohols. But we needed to basically pivot over to these benzimidate radicals to get the totally unbiased aliphatic CH bonds to work. Although you can see a little switch in mechanism here where secondary alcohols don't always give great diastereoselectivity. And of course, chiral information is completely lost after that hydrogen atom transfer. So just to kind of summarize here what we could do with the oxazolines, I think I've reported it previously, so I'll just mention that one transformation here was the DDQ oxidation to an oxazole. This was something that we had gotten some pretty reasonable interest from the pharmaceutical community, and so we decided to look at it a little bit in more depth here. Combination of a nitrile and an alcohol to make these 5-membered azole heteroarenes is not your sort of typical retrosynthetic disconnection. So we decided to expand on it, make it a little bit better. We developed a new acid-based condition to make imidates essentially with any R group we like. But then also it was sort of bothersome that we would use an oxidant, run a column, use another oxidant, do this 2-step sequence. So we got rid of the column. We could telescope it as a 1-pot sequence. But what really annoyed us for the longest time was that this green oxidant DDQ was actually weaker than the original blue oxidant. And so long story short, we figured out a way around this. We could now, switching from sodium iodide to cesium iodide, as well as really crucially acetonitrile to toluene. We could go directly from an imidate all the way to the oxazole via this cascade. I just show some of the molecules we can make down below. So Andrew, who led both the experimental and the computational efforts on this project here, captured these transition states really nicely. So on the left here, you see that 1,5-HAT that I've mentioned all along. You can see the energetics down below are pretty reasonable. But looking over to the right-hand side now, this new intermolecular HAT, this was quite surprising because if you look at the energetics here, they're actually more favorable in every sense. And so we've really been scratching our heads trying to figure out why the second HAT only now occurred in that switch of solvent. And here's our best suggestion for what's going on. In the case of polar solvents, we actually know quite well that beta scission occurs pretty rapidly. So you can imagine that acetoxy radical that affects the HAT can give off CO2, generate a methyl radical. And so that might prevent the second intermolecular HAT. As opposed to now the nonpolar solvent is going to slow down that beta scission, allowing that second HAT to occur and allowing for that double CH functionalization. So it turns out that was actually our second double CH functionalization. We've sort of been obsessed with this idea since the work of Avasay and Ethan, who were interested in intercepting the intermediate halide. So again, we made the imidates, we did beta CH functionalization to get to the halide, and of course we were cyclizing across that halide to get to the CN product. But in this case, what we did was we simply hydrolyzed the imidate off sooner. We could get to the beta CH bond, CH halogen. Or what we could do is we actually calculated that the CH next to the halogen is about 2 kcals weaker than the original CH. And so you can imagine thermodynamically, there'd be some preference for doing a second HAT at that position, getting to these geminal dihalides. So again, just a note on complementarity. The only other beta CH iodonations basically in the world came out of this center as well. The work of Ramesh Giri when he was a graduate student with Jin Kuan Yu. I just highlight one of those examples here with palladium being directed and going after a terminal CH bond, giving primary CIs. And of course, when they pushed the reaction to some extent, they actually got distal diiodination rather than geminal. I see complementarity here, which is reason enough to pursue such a project. And so that's what we did. We developed conditions for mono iodide bromide chloride, as well as the bis halides here. I just show you a family of the geminal diiodides, which are pretty interesting. You don't usually access these all aliphatic diiodides. And so there's some sort of interesting reactivity that we learned in those. We were also a bit surprised that we couldn't get the geminal dichlorination to work, kind of stalled out at the mono. So we said, let's have fun here. We added a little bit of extra halogen and oxidant, and then we could get to these mixed halides in one pot. All right, so the other double CH functionalization story I wanted to tell you was the work of Allen and Raymond. It fits on the same idea that the imidate radical after doing 1,5-HAT gives you a beta iodide. I already mentioned we can cyclize it in polar solvent, or the mechanism that I kind of breezed through was a second oxidation occurs when we have a co-solvent of DCM here, so a little bit less polar, gets to the Ni bond and allowed for that geminal difunctionalization. So what we found lately is we tried to go to less and less polar solvents, but of course we were trying to solubilize the sodium iodide, which was really the major concern here. We found that tert-butanol was a special solvent that could do both of those things, but it actually changed the reactivity a little bit. So it turns out we're oxidizing now the iodine atom to make a hypervalent iodine. Of course, this is an aliphatic one, which is quite different than the bench stable aromatic one up above here. This is a fantastic leaving group. In the literature, it's often referred to as a hyper leaving group or a hypernucleofuge because it's about 1,000,000 times better leaving group than a triflate. And so you can imagine here in this cascade sequence after beta iodination, generation of the triiodide, you could even get sort of an E1 elimination here, or a dissociation of the ions, and then just elimination of this cation here, generate an alkene, and then you could finish off this radical polar cascade with just a 2-electron amino iodination here to get you the same types of oxazolin as I showed you before, but now you also have a gamma CI handle. And so the gray box represents the sequence, but you can even look outside the sequence here, where an alcohol via its imidate has now been converted to this now interesting alcohol that has 3 contiguous carbons with heteroatom substitution. So just a brief look at the types of substrates that we could do affect this now vicinal difunctionalization across cyclic and acyclic alcohols, mostly tertiary, and really it was that E1 mechanism for elimination really helped benefit that elimination, but we could also do secondary at the beta position if we simply biased essentially the gamma position, for example, putting a tertiary group out there instead. And so just showing you what you can do with these oxazolines, you can basically break the CO bond or the CI bond, as I've shown here in red, or you can do both of them here to get to these interesting aziridine alcohol type products. Again, maybe not the most obvious retrosynthetic disconnect from an alcohol to this aziridine, which is basically one reason I love it. All right, so that is it for the double functionalization. Now I wanted to wrap up with our catalysis work. So the delta chemistry, we eventually were able to use catalysts to control selectivity. Copper ended up being one of our favorite catalysts to do this. But in our imitate chemistry, even though we use iodine sometimes in our products, we simply could never affect a catalytic version of this reaction. So again, this is a dirt cheap reagent that we're using stoichiometrically, but in cases at least where it doesn't appear in the product, this really, really bothered us. And so thankfully, Leah, who's emerged as our mechanistic guru in the group, decided to really dive deep into this reaction. And here's basically a summary of what she found. It turns out light was the problem. So the reason we needed so much iodide and oxidant was basically light was breaking apart all of those OI bonds we were making in situ. And simply switching over to a thermal condition, like 50 degrees here, we can now just drop it to just the single equivalent of stoichiometric oxidant, as well as catalytic versions of equivalents of I2, essentially any catalyst loading you want. You can see the kinetics right here. It's a pretty rapid and now well-behaved reaction. And you can see here, having a whole lot less oxidant also allows pi systems now to be tolerated. I just love this alkyne going from 0 to 60% yield, thanks to this switch to catalysis. So another bit of unpublished work from the hands of Allen and Young now. We have found playing a little bit more with the oxidant and adding the base in situ, we can now actually directly go from the alcohol, make the imidate in situ even, and then oxidize it all the way up and generate either these oxazolines or after hydrolysis, these amino alcohols. Actually, we can get to all of the products that I've shown you here now directly from the alcohol without having to pre-generate these imidates. And so the other reason that we actually wanted to do catalysis was really closing the story on interruption. If we start with an NX bond, even on the imidate, we were always forced to recombine that X radical to make a CX bond. And so what we'd hoped to do was start from an NO bond. After a catalytic reduction, generating the O minus and the N radical. After 1,5-HAT, that O minus is going to be an innocent bystander and allow us essentially to do whatever types of functionalization we like at that beta position. And so this was the work of Koki and Stacy. They had this idea, which was a pretty clever one, to start with an acyl chloride looking oxime to make this oxime imidate. And just as a brief aside, from CH functionalization, we could do functionalizations across an alkene. Here's a hydroamination that gives the same types of oxazolines before, albeit hydroamination of alkene here. So there's a nice, again, complement to the work of Overman on these original allotrichloroimidates that, of course, in the 2-electron sense do sigmatropic rearrangements, and now they do hydroaminations in the 1-electron sense as well. And so I just show briefly another set of reactions that we were able to do from these oxime imidates. But the last thing I wanted to tell you about today was the work of this fantastic team to tackle this catalytic asymmetric CH amination here. And really the key was we noticed that when we started with these chiral alcohols, chiral at the beta position after 1,5-HAT, we lost that stereochemical information via this planar radical. And you can see here the isomerized product. And so now with these new oxime imidates as radical precursors, we could use one photocatalyst to generate the end-centered radical. And then after 1,5-HAT, we could now use a different chiral catalyst, such as those copper complexes I showed you before, to intercept this radical and give a diastereoselective reductive elimination to get to these chiral oxazolines. I show the sequence here between these acyl chloride condensation with the alcohol and then copper catalyzed, actually dual iridium and copper catalyzed CH amination. We can get to a variety of these beta amino alcohols in enantioenriched forms with different arenes and heteroarenes at the beta position. But really the generality of this beta position is really fantastic here. You can see alkynes and alkenes are well tolerated, even these Z alkenes, as well as some aliphatic groups, albeit usually on the larger side. And so just wrapping up with the mechanism here, we generate these chiral copper complexes that actually coordinate to these oxymimidates. And so that allows that chiral copper stereochemical information to be nearby. And then when the iridium is excited, it transfers basically its triplet energy over to this entire complex. Then essentially that allows weakening of this NO bond so that the oxygen radical can pop up to the copper in a formal oxidative addition process. And now this copper bound end-centered radical can actually go through both a regio and enantioselective hydrogen atom transfer, and then a diastereoselective trapping of that radical by the chiral copper complex, and then reductive elimination gives this chiral CN bond. After removal, there's our beta amino alcohol. And I've shown you these oxazolines can have HCl removal or reductive or oxidative removal or breaking that CO bond with a halide. And then of course we can do a directed lithiation and generate one type of ligand, or we could take these diols and do a double functionalization and then actually access these new class of what we're calling inverted bis-oxazoline ligands. You can see the oxazoline is inverted here compared to your typical chiral ligand. All right, so that's all I have to show you today. Basically the two programs, the delta CH functionalization of amines via these amidyl radicals, or the beta functionalization of alcohols via these imidate radicals. And these are the stories that I've highlighted today. And so last but certainly not least, I'd love to thank this fantastic team. You can see here, a lot of our interaction is essentially just virtual these days, but you can see they're still continuing with fantastic experimental and intellectual contributions here. Here's the current team. Here's the past team to whom I'm also indebted, as well as funding. And thank you again, Hugh, for this opportunity. Happy to take questions.
Very good, excellent. Okay, we've got some interesting questions for you. So the first one is from Nick Chiappini from Princeton. Awesome talk, 2 questions. With Suzia's work with copper intercepting the nascent radical, have you had any luck with sp3 boronic acids?
I might ask you to repeat the first part, but I'll just say right off the bat, we have not had luck with the sort of, if you're connecting our work with Magnus's talk, methyl boronic acid doesn't work well, as well as some of the first set. But honestly, I think that has something to do with the conditions for transmetallation, just finding the right set of conditions. So we haven't given up yet. We just haven't gotten the hit that I know Nick wants.
Okay, and a more a technical aspect, and for the preparation of the N-fluorine tosamides, is broadest route through the N-chloro compounds with halogen exchange or fluorination with NFSI?
Was the key part of the question, which is broader?
Which is the best way to make the NF tosamides?
Let me read this so I get it. Is the preparation, is the broadest route through, oh no, we go directly from the NH. We just add base and then select fluor. I think that's our most robust method.
Okay, and a question from Grace Panetti from University of Pennsylvania. Can you make similar amidates instead of the imidates to get effective 1,3 activation of amines instead of 1,5?
Can you make similar amidates? Oh, that's right. Amidines, absolutely. We have shown, at least in our oxazole cascade, that double functionalization that we've reported recently, we've shown a couple examples. Turns out amidine synthesis is a little harder to do than imidate synthesis. So I showed you these really nice mild DBU conditions for the most part. Usually you have to use a little harder aluminum trichloride to get to these amidines. So we just haven't made too many of them. But of course, we're working on milder methods to access amidines. And then, of course, like you said, then it's very simple to get to the imidazole and imidazoline type products instead.
Again, a question from Tito Akindele. Did you try a tethered acrylate in the interrupted Hoffmann-Lipfer-Freytag
Oh,
reaction?
how interesting of a question. I can't say that we did. I'm not sure that we took the time to build out that biased substrate. Yeah, as you saw, acrylate was our solvent. And I'll tell you, we used many more biased radical acceptors than acrylate. And so I'll save you the effort of sort of all of those vinyl, sulfonate type derivatives. We tried them all. And as you can see, if there's a halogen radical nearby that carbon radical, it wants to recombine. And so that's sort of the challenge that you have to escape in this interrupted HLF chemistry. Of course, copper is not really a halogen, but it has this really nice, large, relativistically expanded orbitals that function just like the iodine atom, right? And so copper traps these radicals exquisitely fast and kind of does the same chemistry. So I strongly encourage you, if you are thinking about this, to really stay away from the N halogen radical formation, at least unless you're going to go with copper or some other large metal sort of at the end of that first row D block.
Okay, and one final question, another question from Grace Panetti. Is the imidate radical limited to primary alcohols, or can bulky alcohols be used?
Yeah, that's a great question. It's a really subtle question, in fact, because you can see I didn't have any tertiary alcohols. I showed you secondary alcohols, some with pretty good DR, some with not so good. We're certainly working on copper-based conditions to solve those. But the reason tertiary alcohols don't work is not because of the radical reaction. So it's not the imidate radical, it's generating the imidate. So again, kind of going to that same idea that more robust methods to make amidines and imidates are always basically desired, things we're still working on as well. So I believe right now, currently the only tertiary alcohol we've tried in the lab is tert-butanol. And so that gives you a sense of the steric limitations to access tertiary alcohol imidates. But fantastic question. Thank you, Grace.
Okay, great. Well, David, thanks very much for the lovely talk.
Thanks, Hugh.
Okay, so to finish off, we've had a really exciting session, three very distinctive aspects of methodology development related to CH functionalization. Thanks very much, Alison Wentland, Magnus Johansson, and David Nagib. And thank you everyone for joining this event, and hopefully we'll see you again in our next meeting, which is scheduled in May. So once again, thanks everyone, and looking forward to seeing you again. Okay, bye now.